All right, we're going to finish up section 3.1. Shorter, hopefully, video than the first one. I'll talk really fast, or maybe you can understand it. I'll go normal, but we won't do quite as much as the first video. I want to talk about how to do applications with exponential decay. We did a growth example with science, with bacteria growth. We also did a compound interest, looking at money. We'll look at a couple of applications of exponential decay here. We have a car valued at $20,000. It's depreciating. It's losing value at the rate of 8% per year. We want to figure out how much it will be worth in 5 years. Remember our exponential formula, whether it's growth or decay, the general form is y equals a times b to the x power. That a is your initial value. So in this problem, our initial value of the car is $20,000. Now we want this to be a decay model because our car is losing value. We know to be a decay model, this b, this decay, it needs to be a decay factor. The b needs to be less than 1. So to get that b value here, we're going to do something similar that when we did to find the growth factor. We're going to take this 8% and change it to a decimal, 0.08. We're going to subtract it from 1 because we want this to be less than 1. We don't want it to be a negative number. We want it to be a number that's less than 1. So we do 1 minus 0.08. 0.92 is your decay factor. Basically means it's retaining 92% of its value each year because it's losing 8%. And then our exponent will be our variable. In this case, we want to know after 5 years how much this is going to be worth. So I'm going to type this into my calculator. $20,000, 0.92 to the 5th power. And looks like I got $13,181.63. I know we usually keep 3 decimal places there, and it would be 630, but since we're talking dollars and cents, I think it makes more sense to do 2 decimal places. So same idea as the growth application, but now to get your decay factor, you're subtracting this percentage from 1 rather than adding it to 1 like we did in growth. Right? Now a science application, we did bacterial growth in day 1. We're going to talk about half-life today. If you're not very familiar with half-life, if something is radioactive, over time it loses its radioactivity naturally. Comes back to what we call ground state in science. The half-life measures how long it takes for exactly 50% of that substance to return back to the ground state, to decay back into something that is not radioactive. So this is an exponential decay situation. And I took our y equals a times b to the x, and I just tweaked it a little bit. Since we have a 50% decay, to get this decay factor, we would take 0.5, subtract it from 1, and end up with a 0.5 there. The 1/2 is your decay factor in this case. And instead of just putting in the number of years, like we did in the car problem we just did, we have to factor in that half-life. So your exponent here is not just the number of years, or number of time units, but it's that divided by what the half-life is. So basically that'll determine how many half-lives elapse in our time period. And I have an example here about radioactive iodine-131, which I've got a cool true story about. If you ask me about it tomorrow, I'll tell you about an iodine story from working in the labs. You have radioactive iodine is a very short half-life of 8 days, so it's a pretty powerful thing. You have a 200-gram sample. We want to know after 27 days how much will still be radioactive. So we set this up with our initial value of 200 grams. Our decay factor is going to be 1/2. It's going to be 0.5. And now we take that 27 days divided by 8, and that 27 over 8 is our exponent. All right, so we go 200 times 0.5, and we raise that to the 27 over 8 power, and it tells us that after that 27 days, we have 19.278, if I round up, grams that remain radioactive. You can kind of do a quick little check of that. every 8 days, only half of this should still be radioactive. So if you start with 200 grams that are radioactive, after 8 days, we should be down to 100 grams. After another 8 days, we should be down to 50 grams that are radioactive. After another 8 days, 25 grams. So now I've gone 24 days total, 8, 8, 8. I've cut that amount that's radioactive in half each time. After 24 days, I'd expect to have 25 grams radioactive, and a few more days pass and a little bit less of that remains radioactive. So same idea as your growth and decay formula, just getting the half-life factored into that problem. All right, so a couple applications of exponential decay. Something I want you to think about for tomorrow. What if we took the same situation, at 200 grams of this radioactive iodine, the half-life is 8 days. What I want you to think about is how long would it take for this to decay so that only 3 grams remained radioactive at that point? How could we solve that? How could we maybe solve it without using some guess and check strategy? So think about how you might be able to solve that. We'll discuss that in class tomorrow, and we'll practice some radioactive decay and exponential decay application problems.